So hello, yeah, welcome back. Really, I'm now here again, and yeah, to talk about exciting things. Yes, yeah. What I would like to show you in this show, I think it's a bit big of a word, really. Show sounds like it's very planned, and it's really not. It's just me rambling about exciting things, admittedly. Yeah, but what I like to show you is this. Yes, well, no, this is a picture of me. So the big circle is me, tiny circle is what's to come. I should have realized when I drew it. Whatever, shit happens. Yes. Yeah, and I'm gonna keep putting it out there, so I hope you'd like it. Yeah. This is a picture of it. Of course, it's not actually me. This is a representation, and actually, it's a mathematical representation, which I find funny. I'll talk about set theory. What is a set? Well, a set is just some stuff, some certain things. In mathematics, we really like to represent them by circles. Yeah, because you can have dots in your circle. Here we are. I'll just make them. Try and make sure that you can actually see what's going on. So a set could be this set of dots. It's a little bit boring set, but there are a few things we could say about it. You could say that it has 9 dots in it. Yeah, I guess that's about all the funny stuff there actually is about it. We could make it a little bit more exciting and add some more dots. Now it's a set of black and red squares, actually, not dots. Well, yeah. But that's not all. Of course, in mathematics, mathematicians generally like to do sets of numbers, like the natural numbers, 1, 2, 3, 4, 5. Some would say 0 as well. The whole numbers, the rational numbers, the irrational numbers, the real numbers, or the imaginary complex numbers, whatever you fancy, or certain parts of them. But I mean, I think even though it's very broad, I think it's a bit narrow, because really a set could be anything. It could be cars, trees, feelings, people, planets. The only thing is, it has to be precisely defined what is in the set and what's outside the set. So for instance, you can't have a set of all the things that are not in the set. So if you drew a set, and then if someone drew this for me, I'd ask, well, what's going to be in the set? And they would say all the things that aren't in the set. So if I make a dot, this dot is not in the set, so it is in the set. That's a bit, well. So it's in the set, but if it's in the set, then it's not in the set. I mean, if it's inside, it's not on the outside, and then it's not on the inside. And you can see this is something I don't know the English word for. I do encourage you to play around with this, because it can be a lot of fun to just think of different things in sets and what's a set and what's not a set. Well, one set can be a little bit boring, so the next thing, which may or may not be fun, depending on your what you enjoy here in life, would be thinking about more sets. If one set's not fun, then add another one and it will be fun. So let's take 2 sets. Yeah, and what I'd like to be in the first set is, well, all white dots, that won't work very well. Could have one set of red dots. Yeah, red's fine. And one set of black dots. Yeah. These sets are not joined. they don't share anything. Yeah, but that's not too terribly interesting. Instead, we'll make sets that actually do share something, because they can be a little bit more fun. So if I made this set of all the red dots and all the black dots, I want to make dots, and there. So here's one set consisting of all the red dots and all the black dots, and now I want a set consisting of all the this may be difficult. I want a set consisting of all black and all green dots. Yeah. So I draw a circle around the green dots and the black dots, and this is now a new set. The point is now that these sets share something. They share 4 things. Yeah. And sometimes we like to denote what is shared by the set. So if we called, and I guess this is where it becomes a bit more mathematical and actually technical, not just me talking here. If we called the one circle, then the nicer circle, we call A, and the other circle we call B. Then A is the set of all the red and the black dots, and B is the set of the green and the black dots. Well, if we wanted to draw a bunch of blue dots and make a set out of those, we could, of course. But if the set is only consisting of blue dots, then it doesn't share anything with the other 2 sets. But what I want to do is give a name to the set of all black dots, and we could call it D, but there's a smart name for it. Well, at least mathematicians think it's smart. This. What's written, and I can't point at the screen, unfortunately, but I can point with my mouse, at least. This set is the set of all the black dots. What this means is what A and B have in common. Yeah. We could do another one, because these are funny, and these are sort of a language in themselves, and yeah, math is not just something you do, it's a language. You can actually learn to speak maths. Let's just do the A first. Yeah, fine. This by the way, I really hope you can actually see what I'm writing. Yeah, I'm assuming you can. This what all the red, black and green dots. Yeah. See, these are terribly confusing, especially in Danish, where the names are fælles and foreningssæt. I should really have looked up the English names for these. But what can you do? I speak maths, and the sign is universal. So, if you go to Africa, Australia, India, China, America, wherever, a mathematician at least will know what you're talking about. One way to think about these is this is a pot or a bowl that holds everything, and this is something that falls down and chops off bits of the whole thing, so it's only what's in between that is picked. Well, this is an introduction to set theory, isn't it? I would like to consider a set. To actually make this set, I'd have to make some sort of definition. Yeah, I'd have to make a definition of evil is a strong word. Strong word of the not so nice people. I'd like to make a set though of these not so nice people. Depending on what I define as not so nice, I guess we could somewhat agree to putting Hitler in here. Yeah. And this is just to say that the set is not empty. Okay. So, yeah. there are actually some people. When I'm talking about the not so nice people, there's actually some people I'm talking about. I'm not just talking about an empty set, which I guess I haven't talked about before. But if there's nothing in a set, it's empty. That does sort of explain itself, doesn't it? Yeah. So the not so nice people. I think this may be a bit naive, but my naive definition is going to be the people who hurt others. If you kill other people, you're in the group of not so nice people, in the set of not so nice people. Yeah, if you kill someone. So there's quite a few people in here. And just because you're in one set doesn't mean that you're in another. If I had another set, I guess if I don't go too much into the definitions of all that boring stuff, I could just, This other set is going to be mean actions. Murder is definitely in the set of mean actions, at least in my set of mean actions. That I don't want to make it just mean actions, because these two sets are overlapping, so it doesn't. This is a set of people, and this is a set of. If this was a set of actions, they wouldn't be overlapping, because I mean, a person would not be in a set of actions, and an action would not be in a set of people, because then it would be a set of both people and actions, or a set. So I guess this is criminals. This is a lovely set because it has a very clear definition. Those who've been punished by law, they're criminals, at least in the eyes of the law, and for now they are in my eyes as well. I am drawing these two to have something in common, but I am not drawing them over each other, and that's because I think there are. Oh, never mind. I think there are people who are not so nice who are criminals. I think there are criminals, but I think there's also criminals who are not nice. So criminals who are actually nice. For instance, these sort of guys are in movies a lot of times. They will, rob a bank to get money to cure their ill daughter, brother, mother, father, family, friend, whatever. They will steal something. Sometimes the hero steals a motorbike to catch the villain, or anything like that. Yeah, Robin Hood, that's a really good one. He's actually a prime example, isn't he? He's a very good guy, but he's a criminal. Yeah, he's very good example. And then there are also people who aren't very nice, who have killed someone, but who haven't been judged for it. And I would definitely consider them not very nice people, but in the eyes of the law, at least, and in the eyes in this definition, they wouldn't be criminals. Stalin, he actually did kill someone, didn't he? Like, purposefully in those camps or whatever. Let's say, for the sake of the argument, that he didn't kill anyone. At least he wasn't. I guess he was accused, but he wasn't. He wasn't judged for killing anyone. And in some sense of the word, at least, he was not that nice, because he sent a lot of people. Edward Snowden. Oh, Edward Snowden would go in the criminals, but he hasn't killed anyone. Yes. Stalin. Yeah, he sent a lot of people to concentration camps, as you probably know, and he allegedly, at least, let a lot of like millions of people starve. So I wouldn't consider him nice, but he's not actually a criminal. Yeah. Now you may think that this doesn't have very much application. Well, it does have. And the point I'm trying to make is that this is very applicable to the real world. Yeah, and this is maths. It's not directly maths because it's not, calculations, but it's a maths way of thinking about the real world that I think has some strengths. And the strength this has is that you can tell yourself that these, even though sometimes when someone is a criminal, it doesn't mean this way of thinking enables you to distinguish, and it makes sure that you are thinking and not just feeling like it. When someone is judged for being a criminal, we may not always, different people might, other people than me will probably not have the same definition of the not so nice people as me. But often they would put, if someone is judged for being a criminal, in an actual court and stuff, not just by someone, if they're sentenced to jail, they are criminals, and we tend to put them in the group of not so nice people because we think, well, there's a lot of people who are both criminals and not so nice people. There's a bunch of murderers here, and and then when they were judged for being criminals, and they were not so nice people. So when someone's judged a criminal, we sort of think, well, then they must also automatically be not very nice. But that's not always the case. There are people who are criminals, but who are generally nice people anyway. And there's actually also people who are not very nice, but who haven't been judged. And what we tend to think, often anyway, is of something different, called a subset in mathematics. Yeah. Sometimes when there's a set of not so nice people, then there's another set. First I have to tell you something, a little tiny bit of notation, that this set is empty, and I would note that. Do you note that with not that letter, this letter? Yes. Sometimes the line will be vertical, but it's the same sign. Sometimes, if we hear that, and now I'm going to symbolize people with dots because that's easier. We know there's some not so nice people, at least in our view, and we know, and then sometimes some of them are criminals. Yeah. So yeah, this is somewhat accurate for usual thinking. And we sometimes forget that there would be someone out here. If we hear of a lot of people who are criminals and not so nice people, and if we don't hear of any criminals who are nice, then we can forget it, and we just think, well, then what's outside here, that must be empty. I would, with my old proper university mathematics notation, it's with this line that looks like division but isn't. Yeah, so this means, this bit of notation is just a way to write down what is. No, this is complete. This is the wrong way around though, isn't it? This should be the criminals and not so nice people. We tend to think that this is empty. This means the C without what's in NSN. in the group of not so nice people, the set of not so nice people. So that basically means it denotes all which is out here, this moon, half moon bit out here. Because clearly C is not empty, there's something in C, it's just over here, it's in this set. And we can sometimes, if we don't hear about any criminals who are nice, we may tend to think that there's no criminals who are nice, because this would be the nice criminals. We tend to think this is then empty if we don't hear about it. And even when we hear that there are some people in this set, we might think that it's empty. If we just hear about a few people who are criminals and nice, we can sometimes forget that there are nice criminals. For instance, if we only hear about nice criminals in movies, we might think that they are only in movies. There's not any nice criminals out in real life. But I mean, just because you're criminal doesn't mean you've killed someone. Just because you're criminal doesn't mean you're a bad person. 'Cause, I mean, you could have. I mean, there's a bunch of small children all over the world stealing to put food to feed themselves, stealing to feed themselves, and they're not bad people for doing that. They can still be nice people. If this is true, if there were no nice criminals would be a subset of the not so nice people. So once again we have the not so nice people, and the criminals would then be a subset, and you could draw it like this if you wanted. This is a difficult way I've chosen to do my dots. This is if this was the case, if there were no criminals who were nice people. So if all the criminals were not so nice people, then they would be a subset. But they're not, though. That's what we sometimes do forget. Let's just do some proper uni mathematical notation. There we go. This means does not equal. You could do the same thing with not so nice people being the ones who are mean to you, and the ones who act in a mean way instead of criminals. Because what I find anyway is that we often think that the people who are this is mean people, and this is the people who aren't nice to you. You tend to think that the mean people are the same people as the ones who aren't nice to you, and then you can get into the train of thought that if someone does one thing that isn't nice to you, that they're in general mean. But that's not true, because well, we are only humans, and we tend to do sometimes do mean things, and sometimes we do nice things. Keep everything in their appropriate boxes. Can you explain about vectors in space? Vectors in space? A vector, if that's what you want to know, is just an arrow. This is a vector. This looks like a two-dimensional vector, but it isn't. This is a vector. Usually what we do is define a vector by its length in different directions. So this vector would consist of two vectors. One vector in what would usually be the x what you do is you put in coordinates around it, and then I'm imagining a field of squares around this in a big system of coordinates, and then this vector would decompose into two simpler vectors like this. And this looks like a two-dimensional vector, because I only need two simpler vectors to describe it. But in a sense, it's a three-dimensional vector. It just doesn't point out of the third dimension. If you know vectors in the plane, this will... No, this is not a vector in the plane. This is a vector in the plane. It could be 4, 3. So this vector could be this vector, going 4 horizontally and 3 vertically. 4 to the side, 3 up. This is the same as this vector plus another vector 0, 3. These might not look simpler, but as you can see, they sort of are simpler. At least they're considered simpler. Oh yeah, and this could be viewed as a three-dimensional vector with no problem. I would just say, well, this vector is exactly the same as this vector. Go 0 out of the third dimension, so it points outwards to me or to you, but it doesn't point out at all. I could change this, and let's do that just for the fun of it. And now you'll have to, if you want to view it as a three-dimensional vector, you'd have to imagine it going up the screen, and it would go 5 out the screen, so it'd go a little bit more up the screen that this goes out. So it'd start here and then end 5 units out of your screen from this point, directly towards you. Maybe you're aware of the dot product in two-dimensional case. In the two-dimensional case, well, that's really easily expandable to the three-dimensional case. If I had 2 vectors, I'll take specific ones. This will be the first one. We could call this a vector, and this is the tricky bit. It's written as multiplication, but it's not. It's the dot product. 2, 5. So the way you do this, of course, is by 4 times 2 plus 3 times 5. Yeah. So the dot product of these 2 vectors will be 23. Then for a three-dimensional vector, so oh yeah, I guess I should actually say what I'm really doing. You'll notice that it's the top 2 ones multiplied together, added with the bottom 2 ones, and you might then be able to imagine what I'm going to do with the three-dimensional ones. So I'd like to do the dot product of this vector with some other vector. Let's do something where oh, whoops. Yep, and the way to do this, of course, oh, that's wrong, is for the top 2 ones multiplied with the 2 top ones multiplied together, added with the 2 middle ones multiplied together, with the 2 bottom ones multiplied together, added together. Yeah, you'll see. And that'll give 105. So dotting 2 vectors together is a way to go from three-dimensional arrows into just a number. You could actually say, if you watched last time, you could say that the dot product is a function from, and this is where the set way of viewing stuff comes in handy. You could say it's from the set, and this is, I think this is an advanced way of thinking about it. It's not necessary. I just like it. It's from a multidimensional space. The point is, it's from a three-dimensional space into the real numbers. this is, I think, a proper mathematical way of thinking about it. It's very complicated, but it allows you to think about so many things that even though it's complicated, it allows you to understand so much more that it's actually worth it. Yeah, so this is the dot product. Yeah. And you'll go from a vector A, for instance, into a number which would be called x, for instance, if you fancy it. A vector could be two-dimensional, could be three-dimensional. You can add them together, but you can't multiply them together. You have to dot them together. Whereas numbers can be added, subtracted, multiplied, divided, all the things that you can do with normal numbers. Put into other functions and get new numbers. This three-dimensional space, as you might be aware, is often denoted as R3. The R comes from the way to denominate the real numbers. So what's over here would be R. I should really do this. Yeah. I'd like to point out that this is, of course, not restricted to 3 dimensions. This is very much possible in any amount of dimensions. You could do 17 dimensions if you want. You just take the 2 top ones, the 2 number 2 ones, the 2 number 3 ones, the 2 number 4 ones, and all the way down to 17, and you have a dot product. Yeah. Another thing, though, that you can do with vectors in 3-dimensional spaces that is limited to 3 dimensions is taking the cross product, and this involves some slightly heavy maths, so which I won't go too much into, but at least I can let TI do the work for me. Yeah, and this is where it gets embarrassing, because if I have to remember how actually to do this, I'm gonna have to wiki it. Yeah, because it's just a question of memorizing. There's something about these 2 multiplied together minus these 2 multiplied together, then these 2 multiplied together minus these 2 multiplied together, some jazz like that. Yeah. If you want, ask for it. I'll look it up and explain it. If you don't, look it up yourself. And yeah. Well, this is all fun and games. You put 2 vectors in, and you get not just a number out, but an actual vector, which is, of course, already a lot more fun than it was just a few minutes ago. Yeah. Then there's something interesting about this, something that you wouldn't think, but actually is. And if I just say it, probably won't make sense to you. It might not, even when I've explained it, but whatever. Yeah. So what I'll do now is take 2 really, really simple vectors. Because you could actually think about these in your head if you wanted. Because this is just a vector that goes, if I have to use my right, this is a system of coordinates. The x-axis, the y-axis, the z-axis. So the first vector goes 1 in the direction of the x-axis. The second one goes 1 in the direction of the y-axis. And what's interesting then is that the cross product actually goes in the direction of the z-axis. And this is always true. Yeah. So the third one is perpendicular to the 2 first ones, and this is always true. If ever you take the cross product of 2 vectors, the vector you get out will become perpendicular to the 2 first ones. This is very used in physics, I believe. Yes, electromagnetic fields and that sort of thing. And that is all I'm going to say for today. go ahead, tell your friends if they are the tiniest bit interested in maths, or how maths can be applied to the world, and how we can use maths to better understand the world, because that's the real strength that maths